Today we will start fast decoupled load flow. So on last one, during decoupled load flow lectures, we have seen that del pi upon del delta j I is not equal to j is this. We have derived on last one. Similarly, for I is equal to j, we have seen this. And it was homework for you to derive these two and other elements of the Jacobian matrix. Right? So I think you are aware of this. If still you are getting problem how this come, then you can watch my video lectures on Newton-Raphson method of load flow. There I have detailed derivation of all these. So this can further be written as, so in decoupled load flow we had two assumptions. One assumption was Gik is very less than Bik. Second assumption was delta I minus delta j for any I and j is nearly equal to 0. So we will have a third assumption here in fast decoupled load flow, that will be Qi is very less than Vi square Bii. You know what is Qi, you know what is Vi, the same notation, and Pi. So the decoupled load flow assumptions are further extended to one more assumption in fast decoupled load flow. So this can be written as Vi, Vj, Yij. So right here all voltages together Vi, Vj and Yij, break it into sin A into cos B. That will be Yij sin of theta ij. That will be B. What will it be? Yesterday we tried, right? Okay. What was that? Vij and Yij sin of, okay, I am writing again. Yij sin A into cos B, sin theta ij cos delta j minus delta I sin A into cos B plus cos A cos theta ij sin delta j minus delta I. What about this? See, we have all terms from k to n except ith term. If we are going to add ith term and subtract, then that will be nothing but Vic. Sign is here. So Qi. What is Qi? Negative of Vi. K is 1 to n. Yik Vk sign of this. So can we write this as minus Qi? If k is also there, k term, so that will be minus Qi. Is not it? Just see. What is Qi? Qi is negative of all these. So except ith term, all terms are present. So we will add this term here and subtract. So that will be minus Qi minus what it will be? Vi. K is I now, right? So that will again be Vi. So Vi square, and this will be. So we have assumed that this is very small. So that will be 0. Is not it? So that term will vanish. This will not be 0. This will be nearly equal to 1. And what it will be? Sin theta ij, Yij sin theta ij. Bij. So right here, that can be written as minus Vi, Vj, Bij, with all these three assumptions. Isn't it? We have assumed that this is nearly equal to 0, so that term will vanish. So we will have only this term. So this into this Yij sin theta ij, this will be nearly equal to 1 cos, right? So this will be sin theta ij, Yij sin theta ij is nothing but Vij and Vi Vj. Is not it? For this, what we will get? Again, the same term here. Sign of this, right? So again that second term will vanish here. So what we will write? Minus Qi minus Vi into Vi square times Yij sine of theta ij, that is nothing but Bij. So that will equal to Vi square Bij. Is not it? So that will be nearly equal to minus Vi square Bij. Why? Because our third assumption is that Qi is very, very lesser than this. So this term is very, very lesser than this. So we can ignore this term. So finally we will get this. Okay. Bii is not it. We are subtracting ith term, right? K is not equal to I. So from Qi we are subtracting ith term. So Bii. Isn't it? Here also, if you will substitute j is equal to I, it will be minus Vi square Bii. Right? For these two cases. What about these two cases? So what is this?
Yes.
This is Qi. Isn't it?
Yes.
So this will be equal to Qi minus, what is this? Yi sin theta I. What is it? Sine is not D, that is D.
Sine
Reactive part.
Yes,
Is not it? So we will write Vi Bi. What about this? That will be equal to, so that can further be written as Qi is very, very small, so we can neglect wherever Qi is coming out. So we may write directly minus Bii. What about this? Again, break it into sine into cos b, and we have assumed that this difference is very small, so sine term will be neglected, so only cos term will be there, and that will be Yij sine A into cos b, right? Sine of theta ij will be Bij. So this will be minus Vi B Ij.
So I.
Not I.
Also, okay. Yes.
Here this is J.
Okay.
So Yij sin theta ij will be Bij. Clear?
Yes.
Okay. We have done one mistake here. What is formula of Qi? So Qi is Vi times this, is not it? But Vi is not there. So we have missed that. So we need to consider this. We need to consider this. Is not it?
Yes.
So we have included ith term. Now it is fine. Although it doesn't affect, but we need to write it correctly, right? So although Qi is very small, so zero upon something will be zero again, but we missed in earlier, right? Any question till now? No question. So I will run this. Just note down all these values. I will ask you again, or I will utilize this space. So from decoupled load flow, we have seen that del P is nothing but del P upon del delta is not it? From decoupled load flow, we have seen that this power mismatch vector. What is this del P? Power mismatch. Difference between specified. Similarly, Q power mismatch del Q may be written as del Q upon del V. Yesterday we have seen this on last lecture. Del V. from decoupled load flow, we have already these two relationships. And we see that del P upon del delta for the two cases, whether I is not equal to J or equal to J. And similarly, del Q upon del V for the two cases, we have simplified version of these equations, right? So, what is this del P? A column vector. What will be dimension of that? Dimension of that will depend upon number of specified P in the system. So P is specified for both PQ and PV. So except slack bus, if number of buses in the system are n, so except slack bus, the dimension will be n minus 1 by 1. What will be dimension of this? So this is specified for PQ only. So suppose PQ buses are from 2 to m, the same notation. So that will be m minus 1 by m minus 1, right? Number of PQ buses by 1. What will be the dimension of this? Number of rows will be same here also. So once you know the dimension of this, you know the dimension of this, you know the dimension of this. The dimension of this will be number of columns of this. Is not it? You know multiplication rules of matrices, right? So this get multiplied with this, right? Similarly, dimension of this n minus 1 by 1. So dimension of this will be. So delta is variable for both. So again, this is having same dimension n minus 1. So the column will be n minus 1. Rows is number of rows is n minus 1. Number of columns is n minus 1. Is not it? So that you can multiply this n minus 1. So dimension of this will be n minus 1 by n minus 1. That will be a square matrix always. Is not it? So based on this concept, lots of questions are being asked in GATE. We will see after this. So no doubt till now. Fine. So for ith bus, you know that dimension of this is n minus 1. So that will be del P2, del P3, del P up to del Pn. Is not it? So for ith bus, we may write del Pi. Is not it? I may be 2 to n. So del Pi. Del Pi, one element of this vector. So may be written as what you will write? J equal to 2 to n, is not it? Del Pi upon del delta J, del delta J. Just try to understand this. You know del P vector is this matrix into this matrix. So ith member of this will be what it will be? Ith row of this matrix times this vector. So ith row will be del Pi upon del delta J. Is not it? So we may write J 2 to n because for number of columns 2, 3 is not it? N minus 1 in dimension. And we are multiplying each element of row with each element of, and we are adding, is not it? One element of this into one element of this plus, so summation sign. Second element of this into second element of this corresponding to ith row only, is not it? So we may write this, is not it? So, and we know del Pi upon del delta J is, del Pi upon del delta J is minus Vi, Vj, Wij. If you will put J is equal to I, so this will be Vi square Bii, that is here.
Yes.
So we may write this. So del Pi is equal to summation J is equal to J equal to 2 to n, write the values, minus Vi, Vj, Bij times del delta J. Clear to you? We may write. After this, we may write, see, Vi is voltage of ith bus voltage magnitude of ith bus. We are writing active power mismatch for ith bus. So take all ith bus quantities together. So we may write this implies del pi upon vi corresponding to ith bus will be equal to j equal to 2 to n minus vi is gone, so vj bij delta. One more approximation. So in steady state, bus voltage magnitudes are nearly equal to 1 per unit. Plus minus V mean V max, plus minus 5% like that. So that can be assumed as 1 per unit. This is further assumption. So if we are going to assume this Vj, this J is corresponding to J is equal to 2 to n, means bus voltage magnitudes of all the buses can be assumed to be 1 per unit, as in practice the voltages are not allowed to deviate between the limits. It should not be within lower limit or more than upper limit, and then that tolerance is nearly equal to 5% or hardly 10%. So that's why we can further assume it. Why we are assuming? Lots of assumptions are there. We want to make this Jacobian matrix as constant. So it will, the speed of calculation will be faster if it will be constant. Although you will need to get more iterations to get that desired accuracy. It depends on your level of accuracy, level of tolerance you can tolerate. If you can tolerate, then your solution is ready within few seconds, nanoseconds, milliseconds, like that, right? Any doubt? So if we are going to assume this as per unit, so we may further write this as minus this. All quantities in 1 per unit calculation. So 1 per unit. You know how Vj is assumed as 1 per unit, right? So it is gone. So for ith we have written this. So in general we may write del p upon v. Del p upon v matrix, this column vector. Now this will be constant, is not it? Bij is constant quantity. Bij is constant. So we will get one constant, say minus b, some other matrix, name it bp, some other matrix that is constant matrix corresponding to this del p upon, right, times del delta. So what is difference between this and this? Here this is not constant in decoupled, but in fast decoupled this matrix is constant. So we need to evaluate once only, in first iteration only. After that, whatever the value you have obtained in first iteration, the same value will be used in each iteration. So a speed of calculation in each iteration will be faster. Is not it? Similarly, for Qi, so I am writing this. So for Qi, we have del Q is equal to this. Put the values. So del Q is minus Vij, is not it? So using similar procedures, del Q right here equal to del Q upon del V. So again, for which bus we have Q as specified? PQ only. On PQ buses we have assumed, say similar assumption. First one is select bus, and 2, 3 up to M. We assume PQ, is not it? Or M plus 1 onward PV. So we have to write for PQ only. So tell me, this will be say J equal to 2 to M only. Number of, you know how many PQ buses there is. And del Q upon del V will be written as
minus Vi.
Okay, first write this one like this, del Qi upon del Vj. What is this? Del QI we have seen yesterday in previous class. Times del. Are you not getting? Can't be right. For ith bus, ith PQ bus, we may write similar to that. For ith PQ bus or PV bus, we have written del Pi is this. So similarly, from this relation, we may write for ith PQ bus. From this, we may write this. Is not it?
Yes.
And del QI upon del Vj is this one. With these earlier three assumptions. So write it. So that will be equal to j equal to 2 to m minus Vij times del Vj. Clear? Del Qi, or we are writing for ith term. Clear? So that can further be written as, this implies, take all ith quantities, ith bus quantities together. So del Qi upon Vi. So this will be del Qi upon Vi will be equal to, this Vi is gone. So we will get again one constant is not it?
Yes.
Only variable is this. So directly we may write, okay, first write this, then you will get confused. 2 to m minus Vij times del Vj.
Yes.
So this is constant now, right?
Yes.
This quantity is constant. So summing constant terms will be constant. So some constant times this, where j is ranging from 2 to m. So del Vj corresponding, right? So this can be further written as, this implies del Q upon V. This vector, similar to this vector, right? Okay, write in vector because of this I think you are getting. So this vector can be written as, again, some minus, outside or inside doesn't matter. You may write outside also. Corresponding to Q, write this matrix, constant matrix has BQ, some constant, times D. So we have further modified the power mismatch equations for fast decoupled load flow as this. So now it will be easier to evaluate. Procedure will be same as that of Newton-Raphson method of load flow, but we have modified the Jacobian matrix after certain assumptions. So what is harm in assuming these three? You may not get accuracy up to that level, but speed will be faster. But if you will allow for more number of iterations, then those accuracy will be obtained. So number of iteration will be increased, but time per iteration will be reduced. So it is up to you, up to what level you can tolerate, what level of accuracy you want, but it will be faster. The calculation rate will be faster. Is not it? Any doubt till now? So just, yeah, quickly. Tell me.
In both the buses we have assumed Vj is equal to 1 approximately. So why can't Yib also 1?
No, actually we are writing for ith. So we are writing for ith. Ith term is there. So here this also includes ith, is not it? So we are having j is 2 to m. So in between j may be equal to I. Suppose you are writing for 9th bus and number of PQ buses are suppose 20. So 9th bus is also there. So all V terms have been assumed as, is not it? You can assume that also, but as you are already going to write certain quantities for ith bus, so there is no harm in assuming this. Is not it? If you have more assumptions, then the number of iterations needed to get that level of accuracy will be increased. So try to reduce because our objective was just to make this as constant. So if without assuming this as constant 1 per unit, if we are getting our objective, what is harm in assuming that? Is it clear to you? These are assumptions, feasible assumptions, is not it? So try to reduce number of assumptions as low as possible, just in order to reduce. Otherwise, if everything will be assumed, then you will not get, never get.Maybe time required to get your equation will be infinite, means never you will get. So we have to reduce those time also.
आपने दोनों इक्वेशंस एक तो del p वाला और del p by v को कंपेयर किया था, इक्वलाइज किया ताकि आप जैकोबियन को कांस्टेंट को कर सकें, पर दोनों का लेफ्ट हैंड साइड इक्वल नहीं है सर, ऐसे वो
Where I have written equal. Okay, you are talking about these two.
that first equation and the last equation.
First and last. So these equations were obtained from decoupled load flow. These equations were obtained from decoupled load flow. Till decoupled load flow, we had two assumptions. So now for these two equations are for fast decoupled load flow. So we have started from these equations with further one more assumption. What was that? Third assumption that was written, right? What was that? Yeah, less than equal to, very less than vi square bi. Is not it? So after that third assumption, this relation obtained from decoupled load flow is modified as this. And this is for fast decoupled load flow. These two are for decoupled load flow. These two are for fast decoupled load flow. So this matrix is not constant here. This is not constant here. But corresponding matrices, these and these two are constant in fast decoupled load flow. Any other question? Okay, we will quickly solve one problem that was asked in GATE based on fast decoupled load flow. So I am writing that. That question is theoretical one, only to check your concept. No need to calculate. GATE 2015. I am writing the statement of problem. Determine the correctness of the following assertion and the reason. And the reason. So this A is, I am writing here. I am writing reason also. Okay. So fast decoupled load flow method gives approximate load flow solution because it uses several assumptions. This is the statement of this assertion. I am repeating again. The statement of this A is fast decoupled load flow method gives approximate load flow solution because it uses several assumptions. And reason is R. I am writing here R. Accuracy depends on the power mismatch vector tolerance. Repeating again. Accuracy depends on the power mismatch vector tolerance. So options are, option A is both A and R are correct and R is the correct explanation of A. This is option A. B is both A and R are correct, that is true, but R is not the correct reason for A. C is both A and R are false. D is A is false and R is true. So I am repeating the statement of these two A and R. Assertion: fast decoupled load flow method gives approximate load flow solution. That is correct because it uses several assumptions. This is also correct. And reason is, what is the reason of that? Approximate solution. We are getting approximate solution. What is the reason for that? So reason is written: accuracy depends on the power mismatch vector tolerance. Power mismatch vector tolerance. So what is our stopping criteria in Newton-Raphson method load flow? We are going to check these power mismatch with the tolerance. Is not it? For all PQ and PV buses. So for all PQ and PV buses, we are going to check del P. And for all PQ buses, we are going to check del Q. So we are going to check with quantity. Tolerance. So based on that tolerance, accuracy will depend. If you can tolerate more, corresponding accuracy you will get. If you can't tolerate that level of epsilon, then more number of iterations will be required. So accuracy obtained using fast decoupled load flow depends on tolerance of. So that is correct explanation. The appropriate option you can choose. Is not it? Options are not important. Just try to understand the concept and just read. This was asked in year 2015. That's why I am writing. Just have a look on this. So concept wise, are you getting?
Yes.
Any other question? So try to solve some other problems on this.